Bennu's sample is revealing secrets about the early solar system, and maybe even the origins of life. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. NASA's OSIRIS-REx mission returned a pristine asteroid sample that's giving us an unprecedented look at Bennu's chemistry and history. In this episode, we're exploring the first published analyses of the Bennu sample with Scott Sandford, co-investigator on OSIRIS-REx and research scientist at NASA Ames Research Center. Scott has spent nearly 4 decades investigating extraterrestrial materials, and today he's going to help us understand why Bennu's organics and minerals are rewriting what we thought we knew about asteroid chemistry. Then we'll check in with Bruce Betts for What's Up, where we take a look at humanity's history of sample return missions, from the Apollo moon rocks to comet dust and Martian plans for the future. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with awe-inspiring ways to know the cosmos and our place within it. Before moving on to our main story, we have some updates on the exciting lunar missions that launched last week, including Firefly Aerospace's Blue Ghost lander, which landed on the moon on March 2nd, 2025. The Blue Ghost mission is part of NASA's Commercial Lunar Payload Services, or CLPS initiative. It delivered 10 NASA science and technology instruments to the lunar surface, along with a project our organization is super excited about, PlanetVac. PlanetVac is a Planetary Society-supported technology built by Honeybee Robotics. It's designed to collect samples from other worlds. We funded PlanetVac tests in 2013 and 18, and we're really excited to see it finally put to the test on the moon. Someday, we're going to be able to test it on the Martian moon Phobos with the Japanese Aerospace Exploration Agency, or JAXA's, MMX mission. Also last week, NASA's Lunar Trailblazer spacecraft launched as a rideshare payload on the Falcon 9 launch of the IM-2 lunar lander for Intuitive Machines. That was on February 27th. Lunar Trailblazer is led by Principal Investigator Bethany Ehlmann, the president of the Planetary Society's board of directors. The mission is designed to map the amounts and form of water on the moon from orbit. We'll be sharing more about these launches and the other things that launched this last week in future episodes. But now for our main story of the day, the OSIRIS-REx sample return results. On September 24th, 2023, after an intense 7.1 billion kilometer journey, NASA's OSIRIS-REx mission successfully delivered a pristine sample from asteroid Bennu to Earth. The sample, which was sealed in a protective capsule, parachuted safely down in Utah's desert. That is, after it survived a blistering atmospheric entry at 43,000 kilometers per hour, with temperatures rising to 2,900 degrees Celsius. Once it was actually on the ground, the capsule was transported to a clean room at NASA's Johnson Space Center in Houston, Texas, where scientists began analyzing the asteroid's material. Bennu is a near-Earth asteroid, meaning that while it doesn't pose any immediate threat, it could be a potential risk for the future. This makes it a prime target for study, not only for the scientific value, but also for planetary defense. Bennu is a rubble pile asteroid formed from fragments of a larger, catastrophically disrupted body in the early solar system. Even before OSIRIS-REx returned its samples, we strongly suspected that Bennu could contain organic compounds and potentially more volatile-rich material than past asteroid sample returns. But as with all sample return missions, Bennu held more surprises than anyone fully anticipated. With only a tiny fraction of the 122 grams of asteroid material analyzed, scientists are already making remarkable discoveries about the role that asteroids may have played in delivering water and the building blocks of life to planets like Earth. To discuss these findings, we're joined by Dr. Scott Sandford. Scott is a research scientist at NASA Ames Research Center, where he spent nearly 40 years leading research in astrochemistry, astrophysics, and astrobiology. Scott is also a co-investigator on OSIRIS-REx, as well as several other sample return missions, including Stardust, which returned samples from Comet Wield 2. He also worked on JAXA's Hayabusa and Hayabusa 2 missions, which visited asteroids Itokawa and Ryugu, before returning samples to Earth. Today, we're going to discuss the first 2 major papers published by NASA's OSIRIS-REx sample analysis teams, both of which were co-authored by our guest today and released on January 29th, 2025. The first paper, called An evaporite sequence from ancient brine recorded in Bennu samples was published in Nature. It explores the chemical deposits left behind by liquid water on Bennu's parent body, offering clues into the asteroid's early history. The second paper is called Abundant Ammonia and Nitrogen-Rich Soluble Organic Matter in Samples from Asteroid 101955 Bennu. It was published in Nature Astronomy. This research reveals the complex organic compounds found within Bennu's sample, key ingredients that could help us determine the role asteroids played in seeding life on Earth. And who knows, maybe other places. Let's get into the science. Hey, Scott, thanks for joining me on Planetary Radio.
Hi, thanks. I'm happy to be here. I'd love to talk science, and I'm happy to talk with you about it.
And I'm glad to have someone who's worked on so many different sample return missions. OSIRIS-REx isn't the only one that you've worked with.
Yeah, I've been on the Stardust sample return mission, which returned samples from a comet. I've been on the Hayabusa and Hayabusa 2 missions run by the Japanese Space Agency, which went to 2 different asteroids. Then, of course, today we're talking about the OSIRIS-REx mission, which went to asteroid Bennu. And then I played at least a small role in the Genesis mission, which brought back solar wind samples. So I've kind of been involved in, I think, pretty much every sample return NASA's done except Apollo, which was a little before my day.
How did you end up specializing into studying extraterrestrial materials and particularly organics?
I did my thesis work at Washington University in St. Louis, where I was studying cosmic dust that was being collected by U-2 aircraft that were being flown out of NASA Ames here, actually. So they were deploying collectors in the stratosphere at very high altitude and sweeping up some of the dust that was entering the atmosphere from outside. And so these grains are microscopic. They're like 20 microns across, so they're narrower than your strand of your hair. And I was trying to get their IR spectra so we could compare them to telescopic data of comets and asteroids and things. One of the components of these grains we discovered was organics. So organics were of interest to me right off the bat. But in addition, when I came out to NASA Ames, my job wasn't just to work on sample return missions. I was also helping set up the astrochemistry laboratory with Lou Amendola. And this is a laboratory where we can simulate outer space, and in particular, really cold environments where you have mixed molecular ices at really low temperatures. So we're talking about interstellar dust clouds and comets and Pluto and things like, really cold places. And we did work that allowed us to identify some of the components that were in ices out there. And then we also asked ourselves what happens when these ices get irradiated by cosmic rays and photons, because we know that happens in space. And we discovered it drives a whole rich chemistry that turns simple molecules like water and ammonia and methanol into really complex mixtures of things that include amino acids and nucleobases and all these other more complicated organics. And it began to sort of demonstrate to everybody, including us, that it seemed like space is hardwired to do organic chemistry, and it generates a lot of new complexity. And that if you make a new solar system, a new planetary system, odds are that the planets will have this kind of material raining down on them. And so it kind of gives you a leg up on trying to get life started elsewhere. And it also tells you that even where there isn't life, there ought to be organic compounds because these processes are quite universal.
And just the wealth of what was found within this. We'll get into it, but it is absolutely startling. But before we go there, every space mission is a team effort. And in the case of NASA missions, it really does take a lot of different NASA facilities contributing in order to make this work. So how did NASA Ames specifically contribute to the OSIRIS-REx mission?
Okay, so I'm at NASA Ames in Moffett Field in California. I've been with the mission since it started, and so I've played a lot of roles, but in a way you could say Ames has played 2 kind of generic categories of roles. One is Ames played key roles in developing and testing the thermal protection system. I mean, the sample after we capture it is brought back to Earth by the spacecraft, and it gets launched into the Earth's atmosphere, and then it has to survive re-entry, which is what people are probably familiar with. It involves a lot of heat as you come screaming in at something like 14 kilometers per second. So your sample would just burn up if you didn't protect it. And so you need these very special materials that can take that kind of a pounding and survive. And so Ames played a key role in developing these materials and then also testing them at our ArcJet facility here to demonstrate that they work and that they can take the heat, so to speak. And so that was really key. All sample return missions, it doesn't do any good to get the sample if you can't get it to the surface of the Earth and measure it. So this is a key part of all sample return missions, is to have this capability. And so NASA Ames played a big role in making sure that NASA had this ability to do this. And that opens up, all kinds of sample return missions, not just all ones like OSIRIS-REx. And then I've been involved with the mission since the very beginning. I'm one of a handful or so of the original science team members. And so I've had lots of roles over time, and some of this has involved designing aspects of the sampling system or testing aspects of the system, and then, of course, addressing scientific issues. So like right now that the sample is back, that I'm spending my time measuring the samples, which is the main reason I wanted to do this in the beginning. But to get the samples, you have a lot of work to do. And so I played a lot of roles here at ARC in that respect. But I'd also stress, as you mentioned earlier, these missions are complicated, and they take large teams of people who apply all kinds of expertise. And so this kind of thing only works because you have a bunch of really quality people who work very hard for a long time. These missions take, years and years and years. So.
And as we were saying with Genesis last week, it's been 25 years from the beginning of the work to getting it home and then doing all of the sample analysis. But that's what's beautiful about it. As our technology advances, it's actually quite useful to have these samples and analyze them way down the line because we have more capability to do so.
Yeah, there are several beauties to sample return missions, but one of the biggest ones, of course, is you end up with a sample in your lab, not something you're examining remotely on a spacecraft a long ways away. Once you have the sample, then your spacecraft's instruments are effectively all the analytical equipment on the Earth, right? And so you can make measurements of the return samples that you could never make by flying a spacecraft there. There are instruments used to study the Bennu samples that are not just bigger than the spacecraft, they're bigger than the launch pad the spacecraft left from. Okay. And so, so some of the work I've been doing, we've been using the Advanced Light Source at Berkeley, which is a large synchrotron accelerator. And we've been using the X-ray beam there to make measurements. You're never going to fly one of those on a spacecraft. It's a giant building. But since the sample comes back, we can use all these techniques. And that also makes us way more flexible because if you're going to make all your measurements in situ, you have to decide before you send your spacecraft out there what it is you even want to measure. And then in addition, as you mentioned, your technology is by definition sort of state of the art, that even though the mission's taken 10 years, the analytical techniques you're using are fresh and new. And in fact, since you have the sample with you, you can take advantage of technologies that don't exist yet. When we get the sample back, we don't study it for 6 months and say, oh, that was interesting, and then throw it in the trash. No, it goes to a curatorial facility where we take extremely good care of the sample, and it's available for people to study into the future. So I would expect there will be people who will write scientific papers based on discoveries they make from Bennu samples, and some of these papers will come from people who aren't even born yet. Okay, we're still studying Apollo samples and learning stuff about the moon. So once you get the sample back, it's just an amazing resource, and not only for future people, but future techniques that don't exist now that later can be applied.
Each of these samples has taught us a lot about planetary formation and potentially about the history of life on Earth. But this sample is pretty spectacular. What would you say is so special about these samples from Bennu?
Well, I think there's a couple of things that are special about it. You mentioned earlier that, in some ways it wasn't surprising we found organics because we've seen organics in other samples like carbonaceous chondrite type meteorites that land on the Earth. But there's some things about the Bennu samples which are really quite unique. One is that since we went to the asteroid and characterized the asteroid with photography and spectroscopy and all sorts of things, before we went down and got our sample has context. We know where it came from. We know what body it came from. We know where on the body it came from. We know what it looked like before we went down and sampled it. Whereas for meteorites, they're all orphans. They land on the ground. We don't really know where they came from. And so it's hard to put things in context. So the mission gave us this context, and that makes a huge difference. It really allows you to interpret what you're seeing in a much better way. But in addition, we went to great pains to make sure that the sample we brought back was kept as absolutely pristine as possible. So a meteorite, when it lands, we get it for free, sure, but it's an orphan. And oh, by the way, it lands in a pasture or a puddle or bounces off the road and gets hit by a car, whatever. They're basically contaminated almost immediately. And given the abundant presence of water and organics on the Earth, you get contaminated by both of those things. And so there's always this issue when you're measuring organics in a meteorite, particularly if you're measuring any kinds of molecules that are associated with living, biology on the Earth. How do I know this isn't a contaminant? How do I know what I'm measuring is not faking us out instead of being part of the meteorite? Well, in the case of Bennu, since we did everything we could to capture it or to collect it in a pristine manner, we stored it in a pristine manner, we got it back to the Earth's surface in a enclosed container that kept it from rolling around in dirt and so on, then got it very quickly into a prepared clean room, and then the sample has been under nitrogen purge for most of its life, and so it's not exposed to oxygen and water vapor. And so the net result is that when we're measuring things in the samples, we're really quite confident that these are not contaminants. And that makes a big difference, particularly if you're measuring the kinds of molecules that are of interest for the whole astrobiology angle, right? That's a real help. And in fact, I think we're seeing a number of things in the samples we haven't seen very much of in carbonaceous chondrites, specifically because we've kept these things out of air. We're finding things like one of the two papers that came out a few weeks ago is about the fact that we see vaporite sequence, which means we see salts in the samples. And if you have a meteorite land on the Earth with salts in it, and it sits around for a day or two, what happens if you put table salt outside and leave it out overnight, right? It kind of melts away, right? And so this has allowed us to preserve things that probably in most meteorites are lost quite quickly. So all of these things make the Bennu samples just an amazing resource.
What are some of the most useful techniques for trying to analyze the composition of these samples?
Well, I have to be careful how I answer this because I can tell you the techniques I prefer to do the things I do, but that doesn't mean that the other techniques aren't just as valuable for their own reasons. We use a lot of techniques because they're all useful. So some of the stuff I've been using is infrared spectroscopy, and that has two advantages. One is you can compare infrared data to telescopic data or spectral data we took using the spacecraft at the asteroid, so you can compare the two. But it also gives you a lot of information about what molecular components are present. You can tell you if there are organics there, and if so, are they aliphatic organics? Are they aromatic organics? Do they have nitrogen bonds, et cetera, et cetera, et cetera? And we've also been doing this X-ray absorption near-edge spectroscopy work, which also gives us information about that. But there are people who do transmission electron microscopy. It's a great way to measure minerals and understand what their mineral structures and chemical compositions are. A real powerful technique is using isotopics. You study the isotopic ratios of different elements. This can tell you whether the sample contains components that are, in some cases, pre-solar, probably components that actually existed before the asteroid even formed, so they're older than the solar system. In the case of organics, you love to measure isotopics because many extraterrestrial organics are enriched in deuterium, the heavy hydrogen, relative to normal hydrogen, and they're often enriched in nitrogen-15 relative to nitrogen-14. And so if you can measure the isotopic ratios of the organics you're finding in the sample and you get these enrichments, then it's not terrestrial, because terrestrial stuff would have terrestrial isotopic ratios. So that's that's useful for both understanding the chemistry that probably played a role in making them, but it also gives you reassurance that you're looking at the real deal. So isotopics is a big thing. Isotopics are certain isotopic systems can be used to date things. You use them to figure out, this was made 2 million years after this was made, or this was made 4.652 billion years ago, or whatever. So chronology involves isotopics. So isotopics, I don't do isotopic analyses, but I would be the first to stand up and defend them because they're just so useful. And so there's just lots and lots of techniques. I'm sure by the time we get to the end of this mission, we'll have published tens and tens and tens of papers, and they'll all involve at least one, if not multiple, techniques used to study the samples. And again, having the samples back means we can take all these measurements, not just a few, because we're restricted to what the spacecraft can carry. We can take all these measurements, and then you can not only learn from these measurements, but you can now start to compare them together. And then once you get the results from the different ones and put them together, you can figure out things you don't figure out on the basis of a single type of measurement. You may make measurements, say like, this is really strange. I can see a couple ways this could happen, but I'm not sure how to decide which one's most likely. But then you see what someone else has measured and you go like, what you just measured isn't compatible with one of my ideas. That idea is clearly out, And so you learn more than just what you learn from the techniques, you learn by comparing the techniques, and that makes a big difference.
These papers suggest that Bennu didn't just kind of form that way. It actually came from a parent body. What makes us think that that's the case?
Well, several things, but I mean, a lot is just the fact you have a rubble pile suggests that there was a body that was disrupted into lots of pieces and then they got back together. And usually, if you have that kind of an impact that breaks things up, you don't expect necessarily for everything to get back together in one body. So, probably these parts used to be part of a bigger body. But in addition, if you just look at some of the images taken of the surface, the surface was covered with boulders. And you can see boulders that have different characteristics about them, different appearances. Some of them definitely look like they have sort of like layers in them. And a lot of this sort of topography and topology suggests that there was processes going on that involved a bigger body. I mean, for example, we know the bulk of the material we brought back is dominated by a class of minerals called phyllosilicates. These are clays. Okay, so these are minerals that form when you alter previous minerals by exposing them to water, liquid water. And so that implies you had to have had a parent body at one point that was big enough to have liquid water. And it's clearly not there, now. You still have some water molecules in the samples, but there's not liquid water around. And so to get liquid water, you generally think you need to have a large enough body to retain and develop heat in the middle to melt the ices that may have accreted when the body first got together. And so that generally requires a bigger body than the current Bennu to do that. So if you try to figure out where Bennu originally probably came from, there's a couple of families of asteroids that are out there that are reasonable candidates for where it came from. And generally, when you see asteroid families, you assume that's because you had a larger body that broke up and all the parts are now sort of slowly moving apart. So there's a number of lines of evidence that suggest that Bennu used to be part of something considerably bigger than it is now, that we're only seeing a component of that original parent body.
If we could actually go to some of those groups of asteroids and retrieve samples, then we could actually do comparative analysis and see which one is most likely to be part of the parent body that Bennu came from. That's
right. Although one of the nice things about getting a rubble pile asteroid is that, if the original asteroid, let's just, for the sake of argument, say was 20 kilometers across, and we could come down and sample 100 grams of that, okay, then you would have this question, if you had a larger body, how representative of the whole thing is your sample? Could you be biased in a great deal? But if you get a rubble pile asteroid where you've broken up the original one and then kind of jammed the pieces back together helter-skelter, there's a decent chance that the rubble pile will contain components from throughout the larger original body. And so in a way, it's a little bit better grab bag sample, right? So you have the potential for seeing parts of the asteroid that you might not have sampled if you went to any one location before it broke up. And we may be seeing this in the sense that if you look at the samples we brought back, the individual rocks clearly fall into several different lithologies. Not all the rocks look alike. There are some variations between them, and it could well be that that's because some of these came from near the surface of the original parent body and some came from deeper down, or at the very least they had different histories. So I think we're pretty confident that Bennu is just a fraction of a larger parent body. And the hope is that by measuring the samples, we'll actually be able to start telling you a lot of things about the parent body itself. I mean, I think we're already seeing things that give us some clues as to what the environment on the original parent body must have been like, at least in the early solar system and the early going.
Yeah, and you mentioned this earlier that these samples are very nitrogen rich, and especially in ammonia when we compare them to other meteorites and things like that. And they have these isotopic enrichments in the materials too. What does that actually imply about the situation under which Bennu or its parent body formed?
Well, in general, it's thought that in the early, when the solar system formed, it formed out of a protostellar disk. So basically, ice and dust and gas kind of collapsed down on towards the forming sun, and angular momentum ended up forming a disk, which was all this material going around the sun. And of course, the farther you are from the sun, the colder that material was. And in the very early days of the solar nebula, if you were near the midplane of the disk and far out, the temperatures could have been very cold because there's no sunshine on you and you're far from the sun. And so that would have meant that a lot of the gases wouldn't be gases anymore. They'd freeze out as ices. So things like ammonia and carbon dioxide could freeze and make ices. And then when you start to assemble this all together to make a body like the original parent body asteroid, you'd be gathering up not only rocks and minerals, but also these ices. And so your final body would contain both non-volatile materials like silicate minerals, and it would contain volatile materials like these ices. And the fact that we see so much nitrogen and we see these ammonia and so on suggests that we must have formed far enough out that ammonia was condensing. Because if it was warm enough that the ammonia couldn't condense and it was still in the gas phase, then it wouldn't have ended up in the asteroid. It would have just blown away with the gas. So this really suggests that Bennu had to have formed beyond, people talk about the snow line, which is the distance at which water would have frozen. But ammonia freezes at a lower temperature, so does CO2. So probably Bennu formed out beyond those ice lines as well. So this suggests that the original parent body formed in a pretty cold environment at some distance from the sun. And then obviously later, once things settled down a bit, the parent body clearly started to warm up and we started to melt those ices. And then we started doing chemistry and we started doing the aqueous alteration that made the phyllosilicates and so on.
There are a large number of these nitrogen-bearing chemicals inside of these samples, and it's like 10,000 different species are present in the sample, something around there. Is it challenging to try to differentiate between these when you're actually doing the analysis?
Yeah, well, that's a lot of molecules. We see incredibly complex population of molecules. In many cases, it's partly that complicated because we see lots of isomers. So if you have a molecule that contains a certain combination of atoms, just because of the nature of chemistry, you can often bond them together in different arrangements. And so you'll have a molecule, you may have multiple molecules that have the same number of nitrogen, carbon, oxygen, and hydrogen atoms in them, but they're arranged differently. And so this is one way the population is very complex, is you get these isomers, so different versions of a molecule with the same chemical formula. So that's one of the reasons we see all this complexity. But also, on Earth, we have life everywhere you go. And so if you have biochemicals lying around, life is usually not inclined to ignore them, but to eat them, or or if it's another living system, fight with it or something. And so some of this molecular complexity on the Earth is very high because living systems are complex and use complex biochemistry. But there's a certain restriction in the kinds of compounds you see because your life is focusing on the compounds it can use, right? And so in an asteroid where nothing's using these compounds, you could have compounds that are made by abiotic processes, regular versions of chemistry, and then there's nothing to destroy them. And so they hang around. And so you get a really complex mixture because you're not winnowing it down because of the presence of life. And that may be a great thing if you're trying to get life started on a planet. If you're seeding the planet with the kind of stuff that's in an asteroid like Bennu, having an incredibly complex mix sounds like a great idea. You've got all kinds of building blocks to avail yourself of and potentially make use of. So if you kind of think of life as being complex Lego castles that have figured out how to use just the right bricks to make the castle, what objects like Bennu are doing is delivering giant bucket loads of Legos, okay, and of every type. And then when you try to get life started and then it starts to evolve, it can take advantage of the Lego pieces it needs. And there's a good chance they'll be in the box somewhere.
It's so silly, but I'm thinking about the Lego movie, that scene where Batman says, "I only work in black," on dark gray. Bennu's parent body clearly went through this aqueous alteration in order to get all these different compounds, and there are hydrated minerals in this sample, as well as these evaporite sequences that we didn't want to expose to air and things like that. But what does that tell us about the actual fluid interaction inside of Bennu's parent body? Like, how much water do we think was actually present?
Most of the silicates have been converted into these clay minerals. Not all, but a large fraction of them. It's definitely the majority of the minerals are ones that have something to do with this aqueous alteration. So there must have been enough water to do that. But it's also clear that it wasn't like we had a bunch of stones sitting in the bottom of an ocean or something, that as time went on, some of this water was used up by doing the processing of the minerals, and whatever else might have been left over was lost to space over time. And so we don't have the liquid water there anymore. And we have really excellent evidence from the Bennu samples. It was one of the main points of one of these two papers that came out recently, that we see an evaporite sequence. So we see a series of minerals that are the kinds of things you expect to form if you're in a system that contains water and the water is going away, okay, and things are drying out. And so you then deposit minerals in a certain sequence based on how the remaining water gets saltier and saltier. The elements you don't use are concentrated, and you end up with what you call a brine. So people may be familiar with this if they've ever been to places like Mono Lake or whatever, or the Salton Sea, or it's one of these places where the water's really, really salty. You can see evaporites where the water is leaving behind minerals. Where I live, the water's pretty hard. We get buildup on the faucets, right? That's basically the way evaporite. Water leaves and deposits minerals behind. And we see that sequence in the samples for Bennu. So we have really good evidence of this whole drying out process having happened. There's some evidence for this in meteorites, but not nearly as full a sequence, and probably because many of these evaporites are, in fact, things like salts, and they don't hang around if you let a sample get wet or exposed to humidity and so on. We see evidence that water was around and it was abundant enough to cause a lot of changes, but not so abundant to churn everything into clay, and that it didn't stay forever. It ultimately petered away and left behind signs of that in terms of all these evaporites.
We'll be right back with the rest of my interview with Scott Sandford after this short break.
I'm Jack Corelli, Director of Government Relations for the Planetary Society. I'm thrilled to announce that registration is now open for the Planetary Society's flagship advocacy event, the Day of Action. Each year, we empower Planetary Society members from across the United States to directly champion planetary exploration, planetary defense, and the search for life beyond Earth. Attendees meet face-to-face with legislators and their staff in Washington, D.C. to make the case for space exploration and show them why it matters. Research shows that in-person constituent meetings are the most effective way to influence our elected officials, and we need your voice. If you believe in our mission to explore the cosmos, this is your chance to take action. You'll receive comprehensive advocacy training from our expert space policy team, both online and in person. We'll handle the logistics of scheduling your meetings with your representatives, and you'll also gain access to exclusive events and social gatherings with fellow space advocates. This year's Day of Action takes place on Monday, March 24th, 2025. Don't miss your opportunity to help shape the future of space exploration. Register now at planetary.org/Day of Action.
Well, this is all awesome stuff, but I think like the general public, when they were learning about these samples, what really got people excited was all of the organic molecules on board this thing. And what really blew my mind was learning that it had all 5 of the nucleobases that we find in DNA and RNA. We didn't actually find DNA and RNA. That's not what we found there, but all of the building blocks are there. Why is that so significant?
Well, I mean, one of the things that should be pointed out, I talked about isomers earlier. So yes, we see the 5 nucleobases, but we also see compounds that have the same kind of structures of nucleobases. In other words, sure, life on Earth picked these 5, but there are other things that could serve as nucleobases or that have similar chemical structures. And Bennu contains a bunch of those too. Okay, so clearly the chemistry wasn't trying to make the 5 nucleobases you need for life. It was making these kinds of heterocyclic nitrogen-rich molecules like of many types. And that's fortunate because 5 of the ones are the ones that end up being useful for us. So the fact that we see all 5 is really cool, but also given that we see so much of this chemistry having happened, in a way, it's not surprising we got 5 because we really got more than 5. We just assign extra significance to these 5 because, well, heck, I need them to live. But
no big deal.
I think again, this goes back to this issue that it may be that objects like Bennu are great to have land on early planets because they bring kind of a little bit of everything, and then you can rummage through the pile and find out what you need. If you had to come up with an abiotic process which made the 5 nucleobases you need and nothing else, I'm not sure how you would invent such a thing. And so this is true of all the classes of organic molecules we see. I think that if there any of the classes of organic molecules that are of interest because we use them in modern biochemistry, I think in general we're going to or already have found out that, yeah, we make some of those molecules used by biochemistry, and we make a host of other molecules that are in the same class that for whatever reason biochemistry has chosen not to make great use of.
And if we take this a step further, you guys found 14 of the 20 standard protein amino acids that we use in terrestrial life in this thing. And 19 non-protein amino acids were also found in here. So now we have some really solid evidence that even the more complex things that build life are present on these bodies. But then you run into this kind of difficult problem, which is if you did find something like a full nucleic acid, how would you be able to tell if this actually did come from the asteroid and not potential contamination?
Yeah, well, certainly if you'd actually found, there's a huge jump in complexity going from a nucleobase to, an RNA or a DNA molecule. Yeah. So if you found a DNA or RNA, the first thing you should be thinking about is that somehow contamination got in. Yep. In general, the chemistry we see really does sort of go back to this idea that we somehow abiotically made lots of Lego bricks, but getting the really complicated structures maybe takes a planet and liquid water for an extended period. So I don't know, if we saw RNA or DNA in the sample, my first thought would be to worry about contamination, because I would have a hard time explaining how one made that in a Bennu-like environment. But you mentioned the amino acids. It's kind of the same story I told you with the nucleobases. We make a bunch of the ones we see in biochemistry, but we also see a bunch that are not used in biochemistry. So again, whatever chemistry was making these was making a really diverse set of things. And then this diverse set of things could have been delivered to the early Earth. And then this winnowing down to the ones we use in modern biochemistry was probably something that happened on the planet and involved the processes of forming and evolving life. But again, if you're trying to start from scratch, I'd rather have every kind of Lego brick imaginable and
see what works.
A subset. And possible, in fact, that there may be, we don't really know how life got started on the Earth and what that process looked like in detail. And so it's quite possible that there could have been molecules delivered that we don't use in modern biochemistry, but that played a key role in getting things started. And then later life found a better way to do it and decided to abandon part of that scheme. So, I mentioned people have suggested some other possible nucleobases that could have played a role. And some of these other suggestions are actually molecules we produce in great abundance when we do our laboratory experiments. And so it's conceivable that molecules like that rain down out of the sky actually played a role in slightly getting things started. And then once evolution took over and bugs are all fighting amongst themselves for resources and they better tune up fast or become extinct, they decided to abandon some of these ways of proceeding and go to better, more efficient ones. And so it's quite possible that some of these molecules that we don't use in biochemistry now still played an important role in the chemistry. And at the very least, they played an important role in that they delivered carbon, oxygen, nitrogen, hydrogen to the Earth, which you need to make a sustainable biosphere. So even molecules that are not particularly astrobiologically interesting were important to have landing on the planet, because without them, what was life going to live in? What's it going to drink? So a lot of the chemistry that happened was useful just because it turned really volatile forms of nitrogen, carbon, and oxygen, like the ammonia and the CO2 and methane and real simple molecules like that. These never would have ended up on the Earth if they stayed gases. They would have just all blown away. But because chemistry happened and turned them into compounds that can hang around, they hung around, and then they could be delivered to the Earth. And even if they don't end up participating in the actual biochemistry, they're still going to participate in the biosphere. And you need that. So these processes were important, independent of whether they made, alanine or glycine.
I do want to ask you about the chirality of the molecules that we found in the asteroid. But before I do, just for people who aren't familiar with this concept, could you briefly explain it?
Yeah, so chirality, some certain classes of molecules can have what they call handedness. And the best way to explain this is to have, if your listeners can hold up their hands in front of them, they'll see that their hands have the same chemical formula. The chemical formula is one palm, one thumb, four fingers, okay? And your right hand and your left hand have the same chemical equation. but your right hand and your left hand are not identical, right? I mean, the thumb sticks out of the wrong side, or well, the other side. Neither one's the wrong side, so your right hand and your left hand have the same chemical formula, but they don't have the same structure. And so some molecules can do this, and amino acids and sugars are in that class. So amino acids can be left-handed or right-handed. So for reasons we don't completely understand, pretty much all the biochemistry on Earth wants to use left-handed amino acids. And because it's chosen left-handed amino acids, it has to use right-handed sugars because these two have to interact with each other. And so they have to be able to shake hands, basically. So why that's the case is not understood. If I do experiments in my laboratory where I irradiate simple ices with UV photons, I can make amino acids. I can make a lot of different kinds of amino acids. But what I make the amino acids, I make both the right and the left-handed versions in equal proportions. So that means the amino acids have no net chirality, no net handedness. And this is sometimes the word for this is racemic. One of the things we wanted to measure in the Bennu samples is, do we see a net handedness of one over the other? Because if we saw the amino acids in Bennu had a preponderance for left-handed amino acids, that might explain why the Earth decided to go with left-handed amino acids, that it was seeded with more of those than right-handed. And as what we found in Bennu is that the samples have the same amount of each. What that implies then is that the original amino acids were made by an abiotic process, because abiotic processes tend to make equal amounts of the two under most conditions. And then they are all dumped on the Earth, and something happened on the Earth that ultimately picked the left-handed version. And it might have been a coin flip. There might have been a reason why ultimately the left-handed was favored, or it might have been a coin flip, and that we could just as easily on Earth have had the other choice, and everything would be right-handed amino acids and left-handed sugars. So if we ever meet aliens from another solar system, they use the same basic kind of biochemistry we do, which is the use of these amino acids, it's possible they could have the opposite molecular handedness to us, which would maybe have some advantages and disadvantages. We wouldn't be able to eat each other's food, but we also wouldn't be able to eat each other. So there's some advantages and disadvantages there.
That never even occurred to me. That's useful to know, though.
So it's possible that life might have this dichotomy out there. But since we don't really understand how we ended up with the left-handed version here, it's a little hard to assess that. If there's a real reason why, for some reason, left-handed amino acids were preferred on the early Earth to get life started, then that process probably would exist on plenty of other places, and maybe you'd have a net excess of people who wanted to use left-handed amino acids. But it may also have been an environmental thing where, sure, we had a slight thing that favored left-handed excesses, but someone, so for example, you can get a slight difference in right and left-handed amino acids if you irradiate with circularly polarized light. And you get circularly polarized light out of things like pulsars, neutron stars, and things. And so if there was a supernova near where our solar system was forming at the time, and it formed a neutron star that started spitting out circularly polarized light, you'd be getting one circular polarization out of one pole of the neutron star and the other one out of the other pole. And you could end up favoring left-handed amino acids on one side of the neutron star, and in the other direction, you would be favoring the other-handedness. And so you'd find out that the life that forms on this side of the tracks ends up being predominantly left-handed, and life that forms on the other side of the tracks is predominantly right-handed. So, I mean, you can think of various scenarios, but since we don't really know how this happened on the Earth, it's really hard to assess them, but it's pretty fascinating to think about.
So what are some of the biggest questions that you still have left from all of this? And what kind of follow-on work do you personally want to do with these samples in order to answer those questions?
So many questions. Well, I certainly want to, we're finding organics of a number of different kinds in the samples, and we'll want to try to better understand just the range of those. And from that range, also try to work backwards, try to figure out what are the conditions that made these. Were these made by aqueous chemistry, by radiation chemistry? Were some of these organics made before the asteroid even got together and survived? And were some made in the asteroid? Were some of them made even before the solar system formed? So the isotopic results will be interesting to see. If you see large deuterium and nitrogen-15 enrichments in organics, that usually implies chemistry at very low temperatures. And so that could be either imply chemistry that happened in the interstellar cloud from which the solar system formed before the solar system formed, or it could have happened in the solar nebula in the outer regions where everything is really cold. So connecting the isotopic analysis with the organic analysis is going to be really interesting, because this is going to tell us what environments the organics formed in. And my suspicion is what the most likely thing we'll find out is that, well, we formed organics at all of these steps. I mean, we have every reason to believe that the chemistry of all these environments can happen. So in the end, the stuff we're seeing in a sample is the amalgam of things that happened before the solar system existed, formed while the solar system was forming, and that formed in the parent body after the parent body got together. And then all of that ultimately was mixed up and delivered to the Earth. And in the case of our sample, it was delivered by the OSIRIS-REx spacecraft instead of a meteorite. But in the early Earth, it would have been falling down as dust and meteorites, basically.
This has so many consequences for all of our understanding of how water got to Earth and all of the materials for life. But we also have all these other bodies out in our solar system that we still have yet to sample and compare. So my last question to you is, what would you like to see sampled as well so that we can actually do these kinds of comparative analyses?
Okay, well, there's a lot of great cases to go to different places. If you're interested in the sort of early solar system, my favorite place to go next would be to do a similar kind of sample return from a comet, like we did with Bennu. So we did get samples from a comet on the Stardust mission, which I was involved in. But in that case, we got the sample by doing a flyby. The spacecraft flew through the dust cloud around a comet nucleus, nucleus of Wild-2, and it swept up dust. And we did it at a pretty high speed, 6.12 kilometers per second. So that's like Mach 20. So I don't know if you've ever run into anything at Mach 20, but I'm guessing it stings. So the problem is if you try to collect dust at a speed of Mach 20 onto like a metal plate, is what happens is you get a big flash and a bang and an impact, and you have a crater and maybe a little bit of residual material left behind. It's all melted and altered. So we collected it using aerogel, which is the world's lowest density solid. I know that because it's in the Guinness Book of World Records. We put it there. We collected the dust by collecting into this low density solid. And an analogy would be like shooting BBs into a block of styrofoam, right? And because the particles don't come to an immediate stop like they would if they hit a metal plate, but in fact slow down over time, the actual heating is more gradual. And so things can survive that wouldn't otherwise survive. And I think most people have an intuitive sense of this. If I said you were in a bus and the brakes were out, how would you prefer to stop? By running into a sound wall or into a giant pile of pillows? I think everybody's going to pick the pillows because the pillows slow you down more gradually. It's much less violent. Okay. So that's how we captured the Stardust samples, is using this aerogel. And we flew through the cloud and we swept up 1,000 plus grains of dust and brought them back to Earth. And so the sample is like 1,000 grains that are maybe 10 to 20 microns across. So this is a microscopic sample, but we know how to measure microscopic things. And so we learned a lot about comets from that. But one of the things we didn't do as well as I really would want to is to understand the organics, because the impacts were still severe. And so organics are more fragile than minerals, and so they didn't survive as well. And we have plenty of evidence that some of the organics vaporized as the particles hit the aerogel, and those organics then recondensed in the aerogel all around. So we got back some of the atoms, but we didn't have the original molecules. Some of them were altered. And also the amount of material was very small. So all these amino acids we've been talking about coming back from Bennu came out of a sample that was like 6 grams in size. But the entire Stardust sample combined is maybe a milligram. So there's no way to do that kind of analysis with it. So my favorite next mission would be to go to the surface of a comet, touch down, get all that context, just like we did with OSIRIS-REx on Bennu. Measure the nucleus with a lot of techniques, understand where we're going down, then go down and grab 100 grams of material or more, if you can, and bring that back and then study that. And that would allow us to say a lot more about the organics without having to worry about how they were altered by hypervelocity impact into aerogel. And it would give us enough material that we could do some of these techniques like gas chromatography that we did with the Bennu samples that we can't do with the Stardust samples. So that's my number one choice. I think other people might give you other suggestions, but that's what I would vote for.
One of my favorite missions was the European Space Agency's Rosetta mission and the little Philae lander. And I know people will tell me every mission's your favorite mission, Sarah. but really, though, that mission was so cool. And if I think about it in the context of doing a sample return, the things that we could learn and how much fun we'd have along the way, I agree. We need to do that because that would teach us so much. And who knows, give it another decade, 2 decades, maybe we'll be seeing that sample return from a comet that's in your dreams. I really hope
Sample
so.
return missions have so far largely been quite international. I mean, like I say, I mentioned worked on a number of sample return missions. 2 of them were Japanese missions, but they had American involvement. And we had Japanese and Canadians involved in the OSIRIS-REx mission and so on. So I should point out, NASA, when it gets samples back, does a very good job of curating them for the long term so they're available for future science. And anybody can write in a proposal to request samples that they curate to study. And these proposals are then reviewed by a committee to make sure that it's a good use of the sample, that they think the technique will work and that what will be learned will be important enough to justify the use of the material. And if that's all deemed to be good, then this sample is sent to that lab for that analysis. And people from all around the world can request samples. It's not just restricted to the United States. So it is a very international effort, and we take advantage of that by helping share the cost, share the expertise, share the effort.
Well, we're only just beginning to look through these samples. This is just the beginning, and already your team has unlocked so many amazing things. So I cannot wait to see what happens in the future.
Well,
and I really
promise
appreciate
you more. Yeah.
I'm sure. But I really appreciate your time to come on here and explain some of this to
Sure, my
everyone
pleasure.
because, oh my gosh, so cool. I was looking forward to these samples for ages, probably not as long as the people that worked on the mission, but I'm so happy that we finally have them back, that
Yes,
they're safe.
sample
and making
return scientists
science.
have to be patient people.
Really, though.
And you're at the end of the long chain of risks, so everything has to work to get it back. But OSIRIS-REx performed like a champ. Bennu threw us a couple of surprises, but we worked our way through them, and in the end, it did its job by providing us with just a truly amazing samples. So,
Well, thanks so much, Scott.
you're welcome.
And now, for a rundown of the amazing sample return missions humanity has conducted over the last half a century, here's our chief scientist, Dr. Bruce Betts, for What's Up. Hey, Bruce.
Hey, Sarah.
Cool to talk so much about sample returns recently, but we've focused mostly on Genesis recently and now OSIRIS-REx. But there's been a whole bunch of sample returns that I feel like don't get as much credit as they deserve.
Yeah, there are. There are a lot. And going back, of course, to Apollo and bringing back hundreds of kilograms of samples with that, using humans in a rather expensive program that had other goals. But while they were at it, they picked up some great rocks and revolutionized our understanding of the moon and even at some level the solar system. So that was a good start. The Soviets threw in with the Lunar program, which did the first robotic sample returns also from the moon. I like them all. They're all good. Genesis, you talked about, obviously it's good stuff. Stardust, flying through a comet coma, bringing stuff back in aerogel, there's a good time.
Yeah, I don't know as much about Stardust as I should. Like, I know that it was kind of the first, cometary interstellar dust kind of sampling mission, but I don't really know a lot about how it did that.
The summary is a bunch of aerogel, super cool, low dense material, and you open up some doors and you fly through it and stuff goes and sticks in your aerogel. But the real challenge, why the aerogel was so magical, was being able to hit things at kilometers a second and not have them vaporize when you have little tiny particles. So the aerogel would slow them down more gradually. And also leave a track, so you if you look at it at the end of the track will be the particle that's left. But they did, it was cometary, and then they had one on a different part of the spacecraft that was for interstellar grains. And the Planetary Society actually worked with Stardust at home, where people, including our members, go on and work on finding these tracks because the interstellar was particularly a challenge. So anyway, good stuff, great stuff. I don't want to leave out the two Hayabusas doing some a nice asteroid sample return. OSIRIS-REx, of course, great success. The Chinese now with lunar sample returns, a couple of them. A lot of places we haven't sample returned from, but a lot of places we have, and indeed, it's easy to lose track of them.
And I would like to know more about the Chang'e 6 mission samples and how they're different from what we found on the near side of the moon. I know they've done some beginning research and papers on that, but it's only been about a year or so since they did that. So there's a lot left to learn.
Yeah. Okay.
Yeah.
You ready?
Yeah, let's do this.
Random space fact.
I don't know why, but that came off a little Monty Python-esque to me. I want to say one thin mint. Anyway.
When the sun, if you track what constellation the sun goes through over the course of a year, or analogously, the plane of the ecliptic, the Earth's orbit, where it would extend out to, there are, of course, how many constellations? 13.
13. People would say 12, but that's old Babylonian stuff before Ophiuchus entered.
Ooh, you just stole my thunder, but you pronounced it way better than I would have. Well, you played the Babylonian card. That's really awesome. Yeah, they came up with that, divide the sky up into 12 and pretend it means something. But there actually is a 13th constellation, as you know, and it is pronounced how?
Ophiuchus.
And it hangs out along the ecliptic. So go figure. Also, fun that things precess because there's a precession. You end up with the calendar dates changing over time, especially if you go back to the Babylonians time period. So there's a whole lot of changes compared to what they originally came up with in terms of dates and trying to tie it to dates. But yeah, there's poor
Ophiuchus, you got this.
Anyway, it also it hangs out on the ecliptic. There you go. That was I can do this. Ophiuchus rhymes with mucus. Go out there and look up the night sky and think about. No, I can't do that to you. Think about doors. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or, if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members from all over the planet. You can join us and work together to support the sample return missions of the future, particularly Mars sample return, at planetary.org/join. Mark Hilverda and Rui Pauletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.